Okay, so today we're talking about electricity. This is a shorter lesson. Um, don't want to overwhelm you guys with lots of stuff, but I do want to introduce you to some electrical stuff because at the end of the day, if you're working in a greenhouse, you're going to run across it. You're going to run across irrigation with water and controls with electricity. And at some point, you may even have to troubleshoot some stuff. So I want to walk you through just the basics that I think you would need to know if you find yourself in a farm context. So right off the bat, we have to distinguish between high voltage and low voltage. I mean, this seems pretty straightforward, but 110 volts is what you're used to in your household socket, which is already dangerous. But a lot of farms have what's called three-phase 600 volts. And 600 volts is a lot more deadly, and you don't want to play around with that. So be very, very careful about what cabinets you think you can open and should open. So um, examples of high voltage things like pumps, boilers, grow lights, motors, even barn lighting to some extent. Um, I'll get into a little bit later, but one of the reasons why farms like to use three-phase 600 volts is that it's cheaper. I'll talk about why it's cheaper with motors later, but one of the other reasons is that as your voltage goes up, you get away with a thinner wire. So if you were running 110 volts, so let's say, let me actually erase that. Let's say you're running 110 volts here. If you're running 200-meter length, you need a cable that's about that thick. This is the copper inside. That's pretty thick. Otherwise, you end up with almost no electricity at the other end. If you're running 600 volts, right, so 600 volts, that's a much higher voltage. You can use a gauge wire like that. Now, you might say, what's the difference? Well, the difference is if your greenhouse is several hectares in size and you can use thinner gauge cable to wire your greenhouse, you're going to do that because you're going to save a lot of money. Copper wire is very expensive, and when you're wiring a greenhouse, you need to keep that in mind. That's one of the reasons why three-phase hydro is cheaper to operate. So where the realm of you as a grower is concerned is in the low voltage side. So 12 to 48 volts AC or DC is acceptable for you to work with. You don't need an electrician's license to wire that. Um, these would be things like computer controls, which translates into relays, which in turn run water valves, or even light sensors, or rain sensors, any kind of sensor. They're all low voltage. So those things are fine. You're not going to zap your heart if you touch something. It's like a car battery, if you've ever touched a car battery. Or worst case, if you ever stuck a 9-volt battery in your tongue as a kid, come on, I know you have. That's about as bad as it gets. It's nothing. Um, so 110 to 600 volts, steer clear of that, right? You need to be licensed. Um, so typically, the low voltage type stuff in a greenhouse would be in a cabinet, much like this, where there's all sorts of switches and relays. Now, these cabinets, we do have to be careful because there's a combination of both low voltage and high voltage. So obviously, it's ask before you play, but when you're at the college, I'll show you, and I think I've shown some of you in the past what our control panel looks like. And the low voltage uh, switches all they're identified, and they have levers or knobs, and they have shields, so they're safe for you to work with. And that's an important concept to know because sometimes things go wrong with a computer or whatever, and you need to quickly open up a cabinet and flip a switch to make something happen, shade close, vents open, whatever. So it's important to familiarize yourself with how the system works and some of the things to look for. So when we talk about low voltage, there's two kinds. Now, some of this is going to be a review for you if you did any of this stuff in high school, and some of this might be new. There's alternating current and direct current. So AC and DC, just like the band. Uh, and essentially what that means is in DC current, the electricity always flows in one direction, out one side of the battery and into the other. And that's the only way it goes. Whereas with alternating current, it flows this way, and then the next second it flows the other way. And then it just goes back and forth and back and forth. And it does that 60 times a second. So that's alternating current. If you want more help with that, there's a link to a YouTube video that will help you understand it a bit more. But suffice to say, the reason you need to know is because some equipment will not work if it's the incorrect matching. You can't run an AC 24 volt device on a 24 volt DC supply. So you need to know what you have and what you're looking at. So voltmeters come in handy. Here, someone's measuring 25.2 volts. That's normal. It's never exactly 24 volts. This is a standard irrigation hanging basket timer. They all operate on 24 volts, typically AC. Some of the European stuff is DC, and in North America, what seems to happen for some reason is it's AC in greenhouses and DC in landscaping. Go figure. So be careful with that. Landscaping is kind of a mess, but you definitely want to know what you're looking at. And if you're not sure, you can take a voltmeter and you can select it to an AC sensing or a DC sensing. It'll be on the scale. And if you measure 24 when you're selecting the AC, you know you have an AC supply. If you measure 24 when you're looking at the DC setting, then you know you have a DC supply, if that helps. But practically speaking, what does this mean? You're saying, Derek, why on earth are we covering this? One of the most common things I've run into in greenhouses is an irrigation valve fails and someone runs out to the hardware store, buys another irrigation valve, and you quickly install it. Now, if you look at this irrigation valve, it has red and black lines. If you look at this irrigation valve, the lines are both black. So anytime now this isn't always the case, but generally if there's red and black, it means that it has a positive and a negative, which means it's DC. If it's all black, all the wires are black, then it's usually AC because there is no plus minus because it flips back and forth all the time. So that's a really important thing to keep an eye on. I've run into that on a number of occasions, even made the mistake myself. The other area where we see low voltage is in what we call controls. So I've already mentioned irrigation valves. Now, those irrigation valves, the timer, like I showed on an earlier slide, will send out a 24 volt AC voltage to the valve, which then opens it and lets water flow. The Priva or Argus or whatever computer usually runs a 24 alternating current or AC supply out to the valve to open and close it, as an example. Now, the other things that Privas control, like shade curtains, motors that open vents, circulating fans, even turning boilers on, they're also all switched by 24 volt AC circuits. So all the controls are low voltage, right? And the reason they do that is because they can run a little switch on low voltage, which means small, low cost wires out to where they're switching it. And then over here, they have heavy wires going to a large device, big heavy wires. And your computer system switches this little switch, which then in turn switches a big switch. And then the current flows through that switch. That's the purpose of a relay. That's what it does. Okay, so it's little switches controlling bigger switches. It's for safety and reliability that we do that, and we call those relays, okay? How does a relay work? I've got an animation here that's pretty helpful. Essentially, what we have is a 24 volt power supply, 24 volt AC, all right? And when you make contact, 24 volt AC flows through this coil and back around the other side. And it can go this way, and then it can flip and go the other way. It doesn't matter. It makes a magnetic field. This coil pulls this metal plate in, so this plate gets attracted to the coil, which pulls the plunger up, meaning this high power circuit is then switched and current flows through this light bulb. So in this case, we have a situation where we've got a tiny switch up here controlling a very large switch down here. And this side is 24 volts, and this side could be 600 volts, right? So that's the purpose of a relay. And down here are some examples of relays you would see in a greenhouse. What's especially important is because these are removable. If you can actually pull this thing off the panel and replace it with a spare. Invariably, they die on a weekend. I'm introducing this to you because you're going to run into it. Trust me. And it may, you may not remember it all, but it won't be completely foreign to you, the idea, right? So those little relays, that's how they work. This is another diagram, a small switch that sends power to a coil, which generates a magnetic field, which pulls a heavy switch in. And then this large circuit, which could be a pump or a motor or a grow light, is then turned on. So you don't have to worry about where you're pressing your thumb or where the contact's happening, having lots of electricity going through that. It also allows you to send a thin wire to far off to control something on and off, instead of running the heavy wire all the way back to where you are and then all the way back to the equipment. Some close-ups of relays. This is one you might see in your car. So now you can have a look at it. We know that it's DC 12 volts. Cars are not alternating, they're DC. And here it tells you it can handle 40 amps. That's quite a bit of power. It's a good size relay. And what's interesting is now you can understand this diagram here. Let's look at it. These two terminals here energize the coil. This is the coil that generates a magnetic field. So that means terminals 86 and 85 are where you put your 12 volt when you want to switch it on and off. And the other diagrams show you that number 30 is where the electricity comes in, and you have a choice. You can have the electricity flow all the time out here until you energize the plunger and pull the switch down, or the electricity stops and doesn't flow out this one until you energize the plunger and pull this down and make contact, and then you have flow. So that's how the relay works. So you would know which ones to connect for controlling that relay. Here's another picture of a relay. Again, it's a 12 volt relay. Here's your magnetic coil. So these are your terminals that power the coil. And then these are your outputs. So here's your input, number 30 is where the electricity comes in. It's waiting to flow until the plunger pulls down and makes contact, and then it flows across this bridge and out the other side. That's a lot of writing, sorry. Another thing we run into with greenhouses, because we have a combination of AC and sometimes we need DC, is something called a bridge rectifier. That's this square UFO-like thing up here. And what it does is it converts AC to DC. Now, if you look at the picture on the top of this corner here and this corner here have a wavy symbol, and this corner has a plus, and this corner has a negative. And what that allows us to do is we can send in AC current on these pins, right? And it converts it, and out comes on this side negative, and on this side positive DC electricity. So it converts from AC to DC. That's a really helpful thing, especially if you're doing any landscape wiring and you need to convert to DC controls for an outdoor timer or valve. These bridge rectifiers are common in irrigation equipment, and they can die and you have to replace them as well. So this diagram is just showing you what happens. Here the AC is switching from back and forth on this side, and in this bridge of essentially diodes, it forces only DC voltage to come out the other side. I'm not going to get into great big details on this stuff with you guys in exams. This is really just an introduction, right? That's what the technical course is about. I want to talk about electric motors now. electric motors are all over greenhouses. I mean, we have tons. We've got hot water circulating pumps, we've got irrigation pumps, we have pot filler motors, we have shade drives, we have vent drives, we have horizontal airflow fans, exhaust fans. It's all over the place. Lots and lots of motors. And half of these motors are what are called three-phase motors. And three-phase is something that I think I need to introduce you to as well. Um, the kind of electricity that's in your house is single phase, which means if you were to remember, it's alternating current at 110 volts in your socket. And that voltage is going back and forth, up and down, back and forth, back and forth. And that's what we call single phase. So there's the voltage goes up this direction, then that direction, then this direction, then that direction. There's one phase of electricity. When you have three phases, you have one phase, and then overlapped is another phase, slightly shifted, and then a third phase, shifted again. And you end up with sort of a more even voltage coming out, right? And you might say, well, what's the big deal? So I already talked to you about the one thing. Three phase is 600 volts, which is higher voltage, which means you use smaller cables to carry the same amount of power. The second thing is anything that spins more efficiently with three phases as opposed to single phase. Now, the best analogy I can think of is a merry-go-round. So if everyone's sitting on a merry-go-round and say you're this poor chap here and you have to shove this around for the entire birthday party, okay? Now, if there's one of you and you push once every time it goes around, you need a big push to give it enough to go around, and then another big push. So that's kind of like single phase. It's big pushes to make motors turn around. Whereas with three phases, it would be like having this guy and another one over here and another one over here with a simple push, 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 push. There's way less power required to make that merry-go go round. So that is the beauty of three-phase and why greenhouses use it so much. The other thing about three-phase is when a motor goes from standing still to spinning, there's a peak voltage to get that motor going. And what's interesting is three-phase motors are much more efficient at getting motors to go. So the very first few seconds of operation is also more efficient. It's more like this to get it going, as opposed to a single phase where it draws lots of current. And those big start things cost you money in terms of electricity and capacitors and other things that break. So three-phase motors tend to be very, very long-lasting and efficient. They are just good motors. This is me demonstrating a single phase to get a motor going versus the three-phase, where there's a much more even, consistent, oh, my eraser's not going, consistent output, right? So the idea is that single phase requires one big push for a full rotation, where three-phase has three pushes, which makes it easier. Kind of like in a canoe, right? You got one paddle or you got three people paddling, it's a whole lot easier. Or if you're a street performer, it's even easier. Some examples of three-phase motors: irrigation pumps, hot water circulating pumps, the ones that move around in your header loop or out to your zones, even conveyors in greenhouses that move pots around. A lot of those are three-phase. Vent drives, there's usually a motor attached to a gear drive, and this is on a long tube which winds the energy curtain back and forth depending on the time of day. All these motors that you'd run into are three-phase in a greenhouse, which means they're likely 600 volts, which is a definitely do not open and play with, and second, three-phase. So that brings me to my last point, and that is the next time you're out for a walk, look at the hydro poles and you'll see there's 1, 2, 3 wires on the pole. And each one of those is a phase. Now, normally only 2 would go to your apartment or your house. And then maybe these 2 would go to another house. Or these 2 would go to a different house. The electricians figure that all out. But at the end of the day, there is 3 phases. And with farms, all 3 go into the barn, right? So you got all 3 phases to make your motor spin. Now, one of the things I've run across over the years in greenhouses on many occasions is that in the spring, summer, fall, if a thunderstorm happens and you get a lightning strike, right, on one of these things, which is very common, if you look carefully, this bar here is actually it's a fuse, and what happens is when there's a surge from a lightning strike, the bar falls out and it hangs, and this line becomes dead, loses voltage, right? So in the case that it's been hit by lightning, one of them goes, maybe all 3, but usually only one. And what happens sometimes is the greenhouse, the lights in the office, the computers, depending on which phases are powering them, maybe say these 2 are, the office lights stay on and the computers stay on. And you don't realize that there's a problem because the 3rd phase is gone. All your motors will not work. And all of a sudden things start going wrong in the greenhouse and you're confused and you don't really know what's going on. The best thing you can do is go out to the road and look at the hydro pole going into your farm, and you will see one of these 3 hanging, not clipped in. Now, I'm not suggesting you go up there with a pole because you'll die, because that's like 15,000 volts. But then you know that it's not your problem and you got to call the hydro company to come and reset that breaker. Three-phase hydro is a wonderful thing. It saves farms a lot of money. That's why they pay to put it in. But when there's one phase is gone, just about any motor on your farm will stop spinning, and you have problems. So I've at least brought some of this into your brains, so maybe somewhere down the road you remember that, and able to use that. Normally in this lab, I actually spend more time with this board, putting you through scenarios and teaching you how to wire low voltage. I hope to see you at the greenhouse and play with this if we can. It's really not a great big deal. All it is a 24 volt AC transformer that I've just plugged an extension cord onto. And you'll see these wires are all blue, which means it's 24 volts AC. So both wire, doesn't matter. There's no plus, no negative. It's just going back and forth. That goes from a switch, right here, switch into a relay. Now this relay happens to be a 24 volt AC relay. So when I flip this switch, this relay energizes. And what I can do is I can also use the relay to turn things on and off. And so this is the output side of the relay. So I can jumper this over to this fan, for example. And when I flick this switch, the relay makes contact and my electricity flows to the fan and it spins. Or does it? Look carefully. What do you notice about the fan? It has a black wire and a red wire, right? So it's got a plus and a minus. Now, I told you that this is a 24 volt AC power supply. If you send AC to this, is it going to spin? The blades on the fan will just spin briefly and then stay in one spot and sort of fidget or wiggle a little bit, because the alternating current is telling the fan blades to go one way and then the other and one way and the other, and it doesn't spin. It just shakes. So what we have to do to make that fan spin is we have to put this electricity into a bridge rectifier. So we put it in there. Now you'll see there's a red wire coming to this terminal and a black wire coming to this terminal. Now that we have black and red, we can take this wire and connect it to this, and we can take the red wire and connect it to this, and it spins. Now, looking at the irrigation valve, which is down here, is it AC or DC? So if you've been paying attention, you'll notice that the wires are both black, which means this is an AC valve. So we don't need to use this bridge rectifier. We can go directly to the valve. Now, some of you will have noticed that I have LED strips up here. LEDs, look at the wires. We got a red one and we got a black one. So we can't go directly from our power supply to the LEDs. It won't work. We need to have DC. So we go through our handy dandy little bridge rectifier, and we take the red and the black, connect it, and voila, the lights blare. And of course, you can still use this switch and the AC going to this relay, and then switch that to the bridge rectifier, and now you have a switch controlling your LED. So hopefully this introduction, as quick as it was, I don't want to go too far because people's head will start getting frustrated and whatnot, but I think that's all we really need to do for greenhouse exposure. So you have an idea of what AC is, what DC is, you know what a relay is, you know what the black versus black and red lines mean, and you have an idea of what a bridge rectifier is. And I think you know a little more now than you did before. All right. Talk to you later. Bye.